On this page, we see a bunch of problems that are all calculator active. And what that means is that you can feel free to use your calculator to analyze these in any particular way that you think would be useful. We're going to chiefly use our calculator to analyze these by graphing things like the velocity or the acceleration to help us make our sign charts and make our conclusions. So if we start in part A, we want to find the instantaneous velocity when t equals 2. So what we should start by doing is start by finding the velocity function, which is the derivative of position. So we've got negative 3 t squared plus 14 t minus 14. And then what we're going to do is just plug in 2 for the time and see what the velocity at times 2 is. And then if you go through and plug in 2 into this velocity equation right there, what you should end up with is that the velocity is 22 meters per second. Okay, so this means that the particle is heading towards the right at that particular point in time. I just like to say that so that I just kind of have a vision in my head of at time 2, a particle moving towards the right at this particular velocity, 22 meters per second. Okay, so for the next one, we're going to find the acceleration of the particle. So I'm going to want to go one level lower and find the acceleration function by taking the derivative of velocity. So we're going to end up with negative 6t plus 14. And then if I find the acceleration at time 2, we end up with negative 12 plus 14, which is 2 meters per second. Okay, so the acceleration is 2 meters per second, and because acceleration and velocity are both positive numbers, they're both heading towards the right, what that means my particle is doing is that the particle is speeding up. Because both velocity and acceleration have the same sign. If they had different signs, say one was positive, one was negative, that would signify that the particle's slowing down. And if they were both negative, that would mean that the particle is speeding up, just speeding up to the left-hand direction. Okay, so for this last part, part C, what we want to know is where's the particle at rest, when is the particle moving to the right, and when's the particle moving to the left. Now you're going to be very tempted to just take your velocity equation up here and make a sign chart for the velocity equation, because as we've seen up until now, the velocity, a particle is heading to the right when its velocity is positive, and a particle is heading to the left when its velocity is negative. And yes, we will sort of be thinking about a sign chart for this velocity function up there, but that thing is not especially factorable. So what I'm going to ask you to do is to reach for your calculator right now and graph velocity in your calculator in a standard 10 by 10 by 10 window. And you should end up seeing a graph that looks a little bit like this. So what we've got is a parabola that looks like it crosses the x-axis at 2 separate places right there. And remember, this is the graph of velocity, so I'm going to label right next to this parabola that this is the graph of velocity. And I'm going to actually use this to make my sign chart from here. So according to my velocity graph, after 0, we've got a couple places where the velocity is literally 0. The velocity is literally 0 at this point right there. And if you go into your calculator and do second calc 0, you will find that that particular 0 is 1.451. And if you do the same for the other 0, you'll find that the velocity is 0 when t equals 3.215. So these are both of my 2 time values for which the velocity is 0, or when the particle is at rest. So the particle is at rest at both of those times. And then what we can do is we can look closer at my velocity graph over here and try to figure out where the velocity is positive and where the velocity is negative in relation to both of those two times. So as you can see, in between those two times, my velocity graph is literally above the x-axis, so my velocity is positive in that interval. And then before the first rest time, the velocity graph is below the x-axis, so the velocity is negative before that first time. And after that second point in time, my velocity graph is negative. It's below the x-axis, lives in negative land, so my velocity is negative after that. What we're basically doing here is examining this graph for places where the graph is literally positive and literally negative, just like we examined graphs of f prime before to find where the intervals of the function were increasing or decreasing. Except here it's velocity, and we want to know where the particle is going to the right and going to the left, instead of increasing and decreasing. So according to this graph and according to this sign chart, we end up with a few intervals here. So we've got that the particle is moving to the right on the interval 1.451 to 3.215, and the particle is moving to the left on the interval 0 to 1.451 and the interval 3.215 to infinity. And again, because the velocity is literally positive in this space, the particle is moving to the right. And because the velocity is literally negative in these two spaces, we say that the particle is moving to the left. All right, on to the next question, number 5. So what we're given is the position of a particle at any time t seconds, again, with t greater than 0, and we're given this function right there. I'm going to write it down slightly bigger in the space given. So the position s of t equals t squared minus sine of t. And then it gives us a specific interval of time from 0 to 3. And t is measured in seconds and s is measured in meters. And what we're being asked to do here is find the acceleration of the particle at each moment in time the velocity of the particle is 0. So the first thing we should do is find the velocity of the particle. The velocity of the particle is found by, again, taking the derivative of position. So let's go ahead and find the derivative of this position function. The derivative of t squared is 2t minus cosine of t. And then if we want to find where the velocity is equal to 0, we can consider where the velocity is equal to 0. Now this is really, really difficult to solve by hand. And that's where this calculator active thing comes into play. What we're going to do is graph that function in our calculator and then look for zeros. Okay, so what I did is I entered my velocity function into my calculator and I graphed it only on the window from 0 to 3, because I know according to this interval that I only need to worry about times that are between 0 and 3. So I graphed my function in my calculator, and hopefully you did as well, and what I got was a line that looks roughly like this. All right. Now, once I have that graph in front of me, what I can do is I can use the second calc menu in my calculator to look for this 0 right there. So I'm going to do second calc 0, and I'm going to go just to the left of the 0 and just to the right of the 0 and bound it. And then if you hit enter again, you will get that this 0 is at t equals 0.4501 is what we'll say. T equals 0.4501. Okay, so that's where my 0 is. This is where the particle is at rest, because that's where the velocity is equal to 0. So that is when the particle is at rest, where the velocity is 0. And what we want to do is find what the acceleration of the particle is at that point in time. Now, the acceleration of the particle is found by looking at the derivative of velocity. So when we find the acceleration, what we're actually doing here is looking at the slope at that particular point. So let's go in and let's use our derivative knowledge and find what the acceleration would be. So from this velocity equation, I'm going to derive that over here on this side and find what my acceleration would be. The derivative of 2t is 2. And then the derivative of cosine is negative sine. So we have minus negative sine, which would be positive sine of t. And then I want to figure out what the acceleration would be at that particular point in time. So I'm just going to plug in 0.4501 into my acceleration and see what we get. Okay, and if I use a little bit of prediction here, this slope is a positive slope, so hopefully this means that my acceleration should be positive, some positive number, after I plug in 0.4501 in for my t. So let's see. So acceleration at 0.4501 would be equal to, so 2 plus sine of 0.4501, and we get 2.435. Okay, so there's my acceleration. I'm going to tag a unit on it. It's meters per second, because acceleration is the rate of change of velocity, meters per second. Okay, on to the next one. In this particular question, it's doubly important to take notice of what we are being given here. So we are being given not the particle's position function, but the particle's velocity function. We're given it right there. V of t equals cosine of t squared plus t. I'm going to write it right down here. And we're also given a certain time interval to look at from 0 to 2. And it looks like we've got meters per second and seconds again. Okay, so find the velocity of the particle each time the acceleration is 0. Okay, no problem. That means that we need to look at the acceleration of the particle. The acceleration is the derivative of velocity, so let's look there. In order to derive this velocity here, I see cosine of t squared. So we've got a chain rule situation with an inside and an outside. The derivative of the inside layer is 2t. The derivative of the outside, with the inside kept the same, is negative sine of t squared. And then the derivative of the t is just 1. So all told, the acceleration function would be equal to negative 2t sine of t squared plus 1. And we want to know when the acceleration is equal to 0. So let's graph this in our calculators and take a look. Okay, so if you've graphed this in your calculator, you should see a window, and hopefully what you've done is restricted your window to be only from 0 to 2. And then kind of adjusted your y values so that you can get a good, clear picture of what this curve is doing. And on my side, what I see is a curve that kind of looks like this. Goes down, and then back up. So something like that. And we see two different times where this acceleration curve is equal to 0. So I see that the acceleration is equal to 0 right there, and the acceleration is also equal to 0 at that point right there. So what I want to do is find these time values, again, by using second calc 0, and then going through the left bound and the right bound to find those time values. So let's take a look. Okay, after going through and doing the second calc values, it looks like my first time value is t equals 0.813, and my second time value is t equals 1.685. So these are both places where the acceleration is equal to 0. Okay, and then what the problem wants us to do is find the velocity of the particle at each of these two times. So let's take our velocity, which is, again, v of t equals cosine of t squared plus t. Let's plug each of these times into it. So then our velocity at 0.813 would end up being, the velocity of 0.813 would end up being 1.602 meters per second, and then the velocity at time 1.685 would end up being 0.7304 meters per second. Okay, there we go. Let's go on to the next one. All right, this next problem looks very much different than all the other ones, and that's because it almost certainly is. We're not given a position function. We're not even really given any function. What we're given is a graph. And the first thing that I want you to notice, both in reading the problem and also in just looking at it, is that this graph is the graph of velocity. This is a velocity graph. And that is going to tell us certain things easier than others as we go in and answer these questions. So we'll have to think hard and make sure that we know what level of graph we're looking at and whether or not this graph is being used to answer the question in the right way. Okay, so the graph above shows the velocity in miles per hour of a particle moving along the x-axis, just a line from 0 to 11 hours. We've got a semicircle and two line segments. And then part A asks, from 0 to 11 hours, when is the speed of the particle the greatest? Now, the speed of a particle is the velocity without caring about direction. So we don't especially care whether the particle is moving to the right or moving to the left. All we care about is what's the absolute fastest the particle is moving at. And how I want to kind of guide you through this is think about what the speed would be at this particular point in time, right there. So at t equals 2, it looks like my speed would be 2 miles per hour because the velocity at that point in time is positive 2. And because speed doesn't care about the positivity, we say just 2 miles per hour. Similarly, at time 5, it looks like my speed would be about 1 mile per hour. The velocity is about -1, but that only means that the particle is just moving to the left at a speed of 1 mile per hour. Similarly, at t equals 7, looks like my speed would be 5 miles per hour. My velocity is 5 miles per hour to the left, but my speed is just 5 miles per hour. So then with that in mind, the speed of the particle is the greatest probably at the point where, whether you care about positive or negative, just you have the sheer largest number. We're looking for where the absolute value of the velocity is the largest. And that occurs at one specific time value. It occurs way over here looks like at t equals 8. This is the spot where the velocity looks like -6. I don't see any other spots where the velocity is like bigger than +6 or goes lower than -6. So this is where the greatest speed happens. So I'll say that happens at time t equals 6. The velocity right there is -6. So the speed is just +6. Because again, the -6 means that the particle is moving to the left. Okay, let's go on to the next piece. It asks, at which of the times t equals 2, t equals 6, or t equals 9 hours is the acceleration of the particle the greatest? So the acceleration of a particle is found by looking at the derivative of velocity. Or in other words, the slope of velocity. So if we're wondering about acceleration in this problem, we want to look at the slope of velocity. And that's especially important for this graph because this is the graph of velocity. So at each of these 3 times, we'll want to look at the slope of the graph at that particular point. So let's take a look at t equals 2. At t equals 2, looks like we have a slope of 0. So I would say that at t equals 2, my acceleration, which is the slope of velocity, would be 0. At t equals 6, I would say that my acceleration, which again is the slope of velocity, let's take a look. At t equals 6, we are at that point right there. Okay, so we're looking for the slope of this line. Let's go in and calculate it. This point right there is, it looks like 8, -6. And this point right there is 4, 0. So we can use those 2 points to find the slope of this line that's connecting them. So let's do that. The slope between those 2 points would be -6 minus 0 over 8 minus 4. I'm just using y2 minus y1 over x2 minus x1 there. So we get -6 over 4. So -3/2. So it looks like my acceleration there would be -3/2, or -1.5. And let's look at the last acceleration, the acceleration at 9 hours. So the acceleration at 9 hours is again the slope of the velocity at t equals 9. And then what we're going to do is go ahead and look at that particular spot on the graph. So t equals 9 is right there. So let's look at that spot on the graph. And then we're looking for that slope. So this slope looks like it connects the points 8, -6, and this point right there, which is 10, 0. So let's find the slope between those. We would have 0 minus -6 over 10 minus 8. So this would end up being +6 over 2, or 3. So my acceleration at 9 hours would be 3. So from there I can conclude that this is the time where the acceleration would be the greatest. So the acceleration is the greatest at t equals 9 hours. All right, let's take a look at the next one. Okay, and then part C is asking us over what time intervals from 0 to 11 is the particle moving to the left. And as we know from before, moving to the left is equivalent to asking where is the velocity negative. And remember, what we have up here is the graph of velocity. So if you look at this graph, where is this graph literally living in the negative area, in the negative land? And that looks like it's happening over these time intervals. So it looks like the velocity is negative from 4 to 10. Okay, so the particle is moving to the left over the time interval 4 to 10 because v of t is negative. And then the next question here asks us something that's actually a lot different. And just on a first reading, you might think that it's not that much different. It's asking us, where is the velocity of the particle increasing? So this is not asking us, where is the velocity positive? This is asking us, where is the actual velocity of the particle increasing? Or where is the slope of velocity positive? Or if you really want to, where's the acceleration positive? So those are the things that we're looking for. We have the graph of velocity up here. And what we're trying to answer now is, where is this graph increasing? So when I look at this graph for increasing, I see an increasing section from 0 up to 2. And again, I can comfortably say that because it looks like my slopes here are positive from 0 to 2. The slope of velocity is positive over that time interval. And the slope of velocity is also positive, looks like from 8 all the way to 11. So the slope of velocity is positive, means that velocity is increasing. So it looks like I've got 2 time intervals there. One from 0 to 2, and one from 8 to 11. Those are my time intervals where velocity is increasing, or where acceleration is positive. So what I'm going to say is 0 to 2, and then 8 to 11 was, I believe, what the other one was. And I'm going to say velocity is increasing here because v prime, which is acceleration, is positive. Okay. Now E is again asking us a slightly different question, and it's different enough to make us have to really think about what's going on in that original velocity graph. So this is where the, not velocity, but the speed of the particle is increasing. Now if you recall from our earlier discussions, the speed of a particle is increasing when velocity and acceleration have the same sign. So we want to look for spots where the velocity is positive and the acceleration is positive, or where the velocity is negative and the acceleration is negative. And as we look for this, I want you guys to remember that the acceleration is the same as the slope of velocity. So this is going to be kind of a brain bender. We're going to look up at the original velocity graph and look for places where the velocity is positive and the slope of velocity is positive, or where the velocity is negative and the slope of velocity is negative. I want these things to happen at the same time. All right, let's take a look up there. Okay. So just to make this cleaner, I'm going to erase everything that we started with up here. So let's make this graph a little cleaner. Okay. So let's write some things so we want to make some observations where the particle is speeding up. Okay, so again, I'm looking for where the velocity and the acceleration have the same sign, whether they're both positive or both negative. Okay, so I see that from 0 to 4, the velocity is positive, but only on a certain part of it is the velocity positive and the acceleration positive. That's this part right here. So for that particular interval, we see that the velocity is positive because we're living up here in positive space. And the acceleration is also positive because we see positive slopes over that interval. So I know that the particle is speeding up from 0 to 2. Going on the next interval from 2 to 4, I see that the velocity is positive still. The velocity is positive because this graph, which is a velocity graph, is above the x-axis. But the slope of this graph is negative, so that means the acceleration is negative. So this would not be an interval where the particle is speeding up. That would be one where it's slowing down. In the next interval, we'll say from 4 to 8. So what I see through this time interval is I see that the velocity is negative because this velocity graph is below the x-axis. And I also see that the slope over this interval is also negative. The acceleration is negative. So in that time interval, velocity and acceleration have the same sign. So I'm going to add this to our intervals. It looks like from 4 to 8. Okay, and then we're going to have a couple more intervals to check. If you want to, why don't you pause the video for a second and see if you can figure out where would be the last interval where the particle is speeding up. Okay, so the particle is actually speeding up as a last interval from 10 to 11, because this is the interval where the velocity is positive. The velocity is literally above the t-axis there. It lives in positive land. And the acceleration, or the slope of this line, is positive as well. So that's the last interval where the particle is speeding up, from 10 to 11. This part of the graph, the particle is actually slowing down because the velocity is negative, which means the particle is moving to the left, but the acceleration or the slope is positive. So you can kind of see here that the velocities are inching closer towards 0. And when they're doing that, that means that the particle is speeding up. Whereas in this last part, you see how the velocities are branching away from 0 and going up and more positive. That means that they're speeding up. All right, so those are our 3 intervals: 0 to 2, 4 to 8, and 10 to 11. 0 to 2, 4 to 8, and 10 to 11. And again, this is because, and this oftentimes is the most important part of writing these, because I want you to be able to communicate effectively what the reason for your answer is. And that's because both velocity and acceleration have the same sign, positive and positive, or negative and negative, remembering that acceleration is the slope of v of t, the slope of velocity. Okay, and then in part F, at what times is the acceleration of the particle undefined? So the acceleration, again, is the slope of velocity. So we're looking for where the velocity, the slope of velocity is undefined. That's basically going to be places where we have points of discontinuity or points of vertical tangent lines, or any cusps. And you can see that there are certainly a few of those up in that velocity graph. If we zoom up there, we've got, looks like a cusp at 4, a cusp at 8 are our two primary places where the slope is undefined. So we would say at t equals 4 and t equals 8, the acceleration is undefined. All right. And then this last part right here is really stretching us into the next idea that we're going to explore later in the winter. So what I'm going to do here is just basically talk about this and talk about what you would do. So the area of the semicircle on the interval 0 to 4, and if you look at that graph in front of you, the area of the semicircle, which I'm going to call A1, because the semicircle has radius 2, our area of that would be pi times 2 squared, and because it's a semicircle, we take half of that, and that would give me 2 pi. And then if we take a look at the area of the triangle on the interval 4 to 10, I'm going to call that area 2. So for that triangle, we've got an area where we find 1/2 the base and the height. And the base goes from 4 to 10, so that's 6. The height goes all the way down to -6, so the height is 6 as well. And then we take half of that for a triangle, and we would end up with 6 times 6 is 36. Take half of that is 18. And area 3 would be that last triangle from 10 to 11. And again, we've got a base of 1 and a height of 3, and multiply by 1/2. So that gives us 1.5. Okay, now each of these things, what we are basically doing is multiplying two different quantities. In order to find area, what we're doing is multiplying the quantity of the y-axis, and the y-axis is measured in miles per hour. So that's the y's, and we're multiplying that by the thing that we got on the t-axis, or the x-axis, and that was measured in hours. Because remember, this graph up here is a velocity versus time graph, so the y's are measured in miles per hour, and then the x's, or the t's, are measured in hours. So our area is miles per hour times hours. And if we multiply those units together, we just end up with miles. So we see this relationship here, that the area underneath these shapes would give us the number of miles traveled. And that is what all these areas added together means. If you were to add all these things together, what we would end up with is the total distance traveled by the particle. But like I said, that is an idea that we will be exploring in a much deeper level later on in this winter.